Here we go again. Going to continue section 11. Now, just to briefly summarize what I'd already done, on the first page of section 11, we looked at RC circuits. And if you have a capacitor that starts out charged and you discharge it through a resistor, the amount of charge on the capacitor drops off as an e to the minus x kind of thing. It's an exponential decay. The amount of time it takes is indicated by what's called a time constant, which for, wait a minute, no, it was the LR circuit. The amount of current flowing drops off with that exponential pattern. Or if you're just turning it on, it builds up with the same kind of pattern flipped upside down, 1 minus e to the negative x kind of thing. And the first thing we start with today is if a capacitor is discharging through a resistor, which is usually separated from the LR circuits in a textbook by half a dozen chapters. They put the RC circuits in the part that's about electricity and the LR circuits in the part that's about magnetism, and you know, that makes sense in a way, but I like to do them at the same time because it's the exact same kind of behavior. It's the same thing that's going on, just in a different setting, okay? It's somebody basically reading the same story, sitting in a different place as they read it. So what we have this time, instead of a resistor and a coil, we've got a resistor and a capacitor. And let's say the capacitor starts out charged up. Previously, somebody's come along with a battery and a set of jumper cables, and they've hooked it up to the switch is open, so there's no circuit for any current to follow. But a battery earlier, before the moment depicted in this diagram here, a battery was hooked up, which charged up the capacitor to some charge Q on each plate, Q0 we'll call it, and a corresponding voltage between those plates. And then you take the battery away, and at t equals 0, you close the switch. Well, closing the switch establishes a path that charge can follow. There's pluses all over one plate of the capacitor, and there's minuses all over the other plate of the capacitor. Pluses and minuses really like to get together. And so charge starts to flow through the wires, and you know, the capacitor discharges. But just like with the current in the LR circuit on the previous page, this doesn't all happen instantaneously. It takes time for the capacitor to discharge. And so there's, you know, a short period of time when current is flowing before the capacitor is discharged and it stops. But it doesn't stop all at once. It kind of just gradually fades away. So once again, there is a time constant that gives you some idea, you know, some way of rating, does this thing discharge quickly or slowly? And in this case, it's equal to R times C. I could do a similar derivation for this. Remember, for the LR circuit, I set up a differential equation and showed how to solve it. And this exponential equation came out of there. And if I wanted to spend another 5 or 6 or 7 minutes on this, I could do a very similar process for this. But, well, let's not belabor it any more than I already have. The time constant this time is equal to R times C. Basically, what's going on is if you have a larger amount of capacitance, it'll hold more charge, and it takes more time to get it out of there. So that gives you a longer time constant, slightly off center in the box here. And if there is a large amount of resistance in the circuit, well, more resistance means a smaller current flowing, which means it takes longer to drain the charge out of the capacitor. So more resistance, longer time constant. This is the only formula that I put on the formula sheet, the one for charge as a function of time. Well, what if somebody asks you what is the current at t equals 5 milliseconds or something like that? Well, what I expect you to be able to do is take that expression for the charge and be able to say, well, because you're supposed to know the derivative is the definition of the current, I. So you can look at that, take the derivative, which is not a particularly hard thing to do for an exponential function. That gives you the current as a function of time. Or if a question was to ask you the voltage as a function of time, well, that's even more straightforward. You don't even have to know how to take derivatives. You just take this and divide by the capacitance of that capacitor. This expression here is, well, like I wrote over here at the end of the sentence. You take the definition of capacitance, which is another thing that you're supposed to know, and you rearrange it. You multiply both sides by V, you divide both sides by C, so V equals Q over C. And I even wrote down over here what it looks like when you do that. You take this expression, you divide both sides by the capacitance of the capacitor. Well, to the left of the equals, Q over C is the voltage. And over here on the other side, Q original over C is the original voltage. So V equals V0 times the exponential follows immediately from Q equals Q0 times the same exponential in one quick little step. And I didn't think it was asking too much to ask you to understand that. If the capacitor is being charged instead of discharged, if it starts out at 0 and then you connect it to a battery and the battery charges it up, it's just the same picture turned upside down. Just like on the previous page, we had the, here's the current being turned off in an LR circuit. Here's the current being turned on in an LR circuit. It's just the same picture turned upside down. And I didn't bother to draw it again, but here as well, if you're charging the capacitor instead of discharging it, it's the same picture turned upside down. So the time constant would be how much time to reach 63% of the final charge or 63% of the final voltage. And once again, you can, this is just a repeat of what it says up here. Take the derivative if you want the current and so on. So a couple of sample problems to illustrate that. One of them where the capacitor starts out charged, the other one where the capacitor starts out uncharged and builds up. And like I mentioned last time, one of the, actually I just gave an exam to one of my to the Physics 122 class. I was grading some of the papers this morning. And sure enough, just like I told you in the last class, I can't remember if the question was one where you had to use this and somebody used that, or if it was one where somebody used that and they used this. But try not to be the person who does that, because somebody's going to do that. And you'd rather it was, well, I usually say the person sitting next to you, but the person sitting next to you now is probably like your cat or something like that. But anyhow, try not to have it be you. So let's see. 11.2. Part A just asks for the time constant. Well, that's RC, whether it's being turned on or it's being turned off. That's the easy part. If that was a 25-point exam question, Part A would just be like 5 of the 25 points, because there isn't that much to it. You've got, this is a big resistor, although I've got even bigger ones in the back of the physics lab. If anybody wants to see what they look just like any other resistor, except there's a lot of ohms inside of it. So you got 1 mega ohm, and you've got 10 microfarads, and the 10 to the 6 and the 10 to the minus 6 cancel each other, or the mega and the micro cancel each other, if you want to look at it that way. Long time constant, something in the milliseconds is typical, but with so much resistance, the capacitor discharges very, very slowly because it can only push a small amount of current through so much resistance. And so the charge just trickles off of the resistor gradually, and it's 10 seconds. So part B, what is the voltage after 40 seconds? Well, like it says just above the question, delta V is equal to Q over C, and Q in turn since the thing was, it had some original charge Q0 on it, and then you're going to discharge it. This exponential factor here is going to make the charge go down. So the thing in the parentheses is the charge Q at any time t. I substitute that in for Q, and this once again is a rearranged version of C equals Q over delta V. So just like, actually, I'm just completely repeating what it says over here. The Q0 over C is V0. Because, you know, if V equals Q over C, it follows that Q0 over C is V0. Or delta V0, maybe I should call it. I don't know. I suppose I probably should. So starting with what's available to you on the formula sheet, which is the thing in parentheses, that's how you get volts as a function of time. And fill in the numbers. Original voltage, 500. It's up there. We want to know the voltage at t equals 40 seconds. So that 40 is what goes in for t. Tau is the time constant, that's the 10. So e to the negative 4th power, another mistake that actually I've seen more than once. Somebody else on that exam this morning had it all set up perfectly, but she forgot the minus sign when she went to punch it up. So sometimes things like that just can't be helped, though. I do them from time to time myself. So you got this little number times this big number, and there are some devices where capacitors have high voltages on them like that. One example that comes to mind is a microwave oven. They've got some big capacitors in there, and if you ever go, for some reason, taking a microwave oven apart, I have this tendency before I want to throw anything out, it's like, I want to look inside it for a minute. Maybe it's just a wire I can solder back on. And once in a while I get lucky and it is. Usually I just end up wasting an hour. But you want to be very careful because you can get a very dangerous shock out of a microwave oven after it's been unplugged. Because, you know, if you got a capacitor with 500 volts on it, yeah, you could get a pretty significant shock off of something like that. So anyhow, that was after 4 time constants, it's down to 9 volts roughly. Number 3. This time it starts out uncharged. We're just going to hook it up to a 9-volt battery like you might have in a little portable radio or something like that. Some of the meters I use in the lab use 9-volt batteries, the digital multimeters. So no shock hazard this time. You may be aware of this, but you know how you tell if a 9-volt battery is any good? You stick it on your tongue. I've done it 1,000 times. If you get a little tickle off of it, so somewhere in the teens of volts, you really don't want to do that. It starts getting kind of uncomfortable, but for 9 volts, it's just perfect. If you get a little tickle off of it, it's a good battery. If you don't, you throw it in the trash. Anyway, this time the only resistance in the circuit is the 0.5 ohm of internal resistance in the battery. Well, there's probably a few tenths of an ohm in the wires too, but well, we'll say that's included in the 0.5. Anyhow, for a battery or for a capacitor that's being charged up, Q equals C times the EMF. C times the EMF is the final charge on the capacitor, okay? That also, definition of capacitance, C equals Q over delta V. So charge equals C times the voltage. Well, the final voltage is that the capacitor will build up to the EMF here is the 9 volts of the 9-volt battery. And in the end, the capacitor is going to build up to that 9 volts times the capacitance from this. That means that these two things together are the final charge that it reaches as time approaches infinity. So the charge at any time t equals the final charge that it's eventually going to reach times 1 minus e to the negative t over tau. And as I said, the full charge so when it says how long will it take to become 90% charged, we're after the value of t when the charge is 90% of this thing that I just wrote down. So 90% implies that at the time we're interested in, Q equals 0.9 times C times E. So fill that in, and the rest is math. And you divide both sides by CE, and that's gone. So 0.9 equals 1 minus the exponential. We'll do a little switcheroo here and say that e to the negative t over tau equals 1 minus 0.9. Okay. Added the exponential to both sides, subtracted the 0.9 from both sides. And of course, 1 minus 0.9 is 0.1. So my objective here is to solve it for t. Question is, how long will it take, meaning how much time will it take And so to get that function off of the t, I apply the inverse function. The inverse function of an exponential is a log, so I take the natural log of both sides. Natural log of the exponential, the two functions cancel each other out because they're inverses, and you're left with just the negative t over tau. And so up until now, I've just been writing tau over and over again, but I'm going to need a number. Well, I can just do it all at once. Let's finish it off. T equals negative tau times log of 0.1. The time constant is R times C. R is 0.5 of an ohm. C is 10 to the negative fifth of a farad, 10 microfarads. Natural log of 0.1 is negative 2.3. And here's the part where you use the calculator. So 1.15 times 10 negative fifth seconds, or what might be a more convenient way of saying it, 11.5 microseconds. And we've done another page. Next topic, magnetic and electric energy. One place where this becomes significant is when you get into a discussion of electromagnetic waves. When we do that unit on electromagnetic waves in Physics 3, the energy carried by light, or for that matter, any other kind of electromagnetic radiation, the energy per unit volume in say a beam of light is this plus that, okay? Light is made of electric and magnetic fields. The electric field in a light wave carries that much energy. The magnetic field carries that much energy. And I said it backwards. This one's helps if you look at what you're talking about. Magnetic field, electric field. Anyhow, you add those two things together, and that's the energy content of the light. That would be one place where this is relevant. But as far as justifying the expressions in the first place, understanding where they come from, well, as is often the case, I'm not going to do a really general, rigorous derivation. I'm just going to talk you through how you would illustrate this in a convenient special case, and then after I've done that, say that the result is true in general. The convenient special case for a magnetic field, as usual, is a solenoid, because inside of a solenoid, you have a uniform electric field, which is something you can deal with using 9th grade algebra instead of having to integrate, because things vary from one point to the next. So let's consider a solenoid, which is, see, actually, I guess I don't get down to making it a solenoid until I get to here. I guess this first part is general. Any old coil, wind some wire around a rubber duck. I don't care what shape it is. It becomes later that we have to have a solenoid. So whatever kind of coil it is, starts out with no current in it, and then you turn it on. And over the next short period of time, the current builds up like I was talking about a couple of pages ago. Let's take this buildup and divide it into many tiny little increments, okay? Just like millionths or billionths of a second, eventually we're going to take the limit where the time intervals become, they approach zero. But let's consider the amount of energy added to the magnetic field by each little increase of the current in the coil. Well, the voltage induced across the coil is LdI dt. We've thrown that equation around several times by now. Power. Power means energy per unit time. So going with just an infinitesimal amount of time where an infinitesimal amount of energy gets added, energy per unit time is power. Power is watts, which we saw earlier in the course is equal to volts times amps. So LdI dt is equal to the voltage. If you put that in for V, then the dt's cancel out, and you're left with this. As the current increases a small amount, the energy stored in the magnetic field around that current increases by this small amount. And then you integrate from 0 to the final current. The integral of I to the first power is 1/2 I squared. And the moral of the story is that the energy stored in the magnetic field of a coil is 1/2 Li squared. Now here's the part where we want to talk about the energy density rather than the total energy. The energy density being the more useful thing if you're talking about a beam of light or something like that. Energy per unit volume. Well, I never really bothered bringing this up earlier, but if you dig around in the textbook, and at least at one time it was chapter 32. I'm not sure if I've checked that in the last couple of editions. Maybe it's chapter 31 or 33 now, because they do like to mess with that sort of thing. But, well, if you really want to find it, use the index. Anyhow, somewhere in the textbook it says that the self-inductance of a solenoid is this formula here, where I've used capital L for inductance and a lowercase l for the length of the solenoid. I made it a script L because if I just used this font here, it would look like a 1 and nobody would ever figure out what I meant. So that goes in for L. The volume containing that energy would be the volume inside the solenoid, and that's its cross-sectional area times its length. So, you combine a few things, the two L's combine into an L squared and so forth. And then you can rearrange it some more, like mu squared, oh, the lead's sticking out, I didn't want to do that. Mu squared over mu is equal to the mu I had over here. This mu is the magnetic permeability, not to be confused with the magnetic moment, which we're also using the Greek letter mu for, or for that matter, coefficient of friction. If there was a vacuum inside the coil, this would be mu naught, 4 pi times 10 to the negative 7. But I wrote it like this because, what if there's a piece of brass inside there rather than an empty space? Well, then you have to use the permeability of brass. Anyhow, mu naught In over L is the magnetic field inside of a solenoid. That part is on the formula sheet. I've used that one several times. And so from that illustrates that the energy density, the number of joules per cubic meter, is 1/2 mu naught, if it's empty space, times b squared. And I'm going to do an example, but I might as well just keep talking and then do both examples at once. If you want an expression for the energy in an electric field, it's a similar kind of argument. This time you consider a parallel plate capacitor because that's where you get a uniform electric field. It makes the math easier. If the capacitor starts out at 0 and you consider charging it up a small amount at a time, you integrate, kind of like how I integrated this to get that, and it turns out 1/2 CV squared, where V is the voltage between the plates, is the energy in the electric field of that capacitor. Or using the definition of capacitance, C equals Q over V, actually be the other way around. I put in, if you rearrange this, it becomes V equals Q over C. You put Q over C in there where the voltage was, and some of the C's cancel out. And if you want it in terms of the charge, it's this. And if you want it in terms of the voltage, it's that. So that's the total energy stored in the capacitor, energy per unit volume. You divide by the volume inside the capacitor, much like I did with the volume inside the solenoid, and you get this, where epsilon is our permittivity constant from Gauss's law, epsilon 0 if you're in free space. So a couple of examples. The Earth's magnetic field, typical value is somewhere around, several tenths of a Gauss. 0.7 would be fairly realistic. So the question is, how much space you have to be talking about for it to contain a joule of energy in its magnetic field? So 11.4. By the way, this is kind of a one-sided sort of thing. If you have any questions as we go along, I spend a lot of time these days looking at email. You might as well join in. Or if you want to have a really extended conversation about something, we could even work out a phone call. But I figured it was, aside from the fact it's easier to make a recording, I figured it was probably what you guys preferred rather than some sort of live Zoom meeting, because, if you want to go to physics class at 11 o'clock at night, you can go to your physics class at 11 o'clock at night this way. Anyhow, energy per unit volume. I'll use these symbols here, and I'd better carefully label that as volume. Otherwise, somebody's going to think it's voltage or velocity, or I don't know what else starts with V. U for energy. We've used that notation a lot. So you look at the note packet, the page I was just showing you, or on your formula sheet. It's 2 mu naught. If we want to talk about, the Earth's magnetic field just above its surface, we'd be talking about a magnetic field in air. The permeability of air is extremely close to the permeability of a vacuum. So unless you want to go to a whole lot of decimal places, we can just use mu naught for mu. And how much volume contains 1 joule? We want to solve for V. So rearranging a little bit, you multiply both sides by V, you divide both sides by B squared, you do a bunch of stuff like that, and the volume is going to be 2 mu naught times U over B squared. Fill in numbers, punch it up. That's all there is to this one. How much volume contains 1 joule? So you put that in for the energy U. Remember, a Gauss is not an SI unit. If you're going to have this come out in cubic meters, then you need Teslas. So that's 0.7 times, there are 10 to the 4th Gausses per Tesla. So 0.7 times 10 to the negative 4th, 7 times 10 to the negative 5th, whatever seems like a good way to write that. Don't forget to square it like I almost did just now. And it comes out 513 cubic meters, which is, you know, if it's a cube, that would be about 8 meters on the side. And so we're talking about a volume 2 or 3 times bigger than the physics lab. The physics lab's probably something like 8 meters on a side, but it's not 8 meters tall. So the magnetic field from the Earth in the physics lab contains somewhere in the neighborhood of 1/3 to 1/2 joule worth of energy, which isn't very much. But on the other hand, the Earth's field occupies a lot of cubic meters if you think about the whole planet, and it kind of adds up. Number 5. How much voltage has to be applied to a 50 microfarad capacitor if you want to store 1 joule in it? Okay. This one isn't about the energy density. We're not going to get involved in the volume in any way. 1 joule is simply the energy U. So the energy stored in a capacitor is 1/2 C times delta V squared. And it says we want to store 1 joule in this capacitor. And it says it's a 50 microfarad capacitor, 5 10 to the negative 5th of a farad. And I suppose with all these V's floating around, I should probably carefully label that now I'm talking about voltage. So both sides times 2, both sides divided by that, take the square root. $200 volts. So a lot of 50 microfarad capacitors won't take 200 volts. I mean, if you look at the writing on a capacitor, it says something like 50 microfarads, and then it might say something like 25 volts or something on there. What that voltage is that's the breakdown voltage, somewhere in the vicinity of however many volts it says on there. The capacitor will experience dielectric breakdown, meaning a spark jumps from the one plate to the other, and the capacitor discharges. And this limits how high you can go with the voltage on the thing, which limits how much energy you can store in it. So a 50 microfarad capacitor that can still function at 200 volts would be, well, it's not the biggest capacitor anybody's ever built, but it would be relatively large, which is the reason that when you want to store large amounts of energy, it's batteries, not capacitors. Okay, you'll notice that electric cars are powered by batteries, lithium-ion batteries, I believe, rather than big banks of capacitors. Each has its advantages, okay? Batteries will store significantly more energy on the one hand. What capacitors have going for them is speed. You know, if you're driving around in your shiny new Tesla and the gauge is getting down toward empty, you have to stop for a little while to recharge the thing. Well, if you were planning to eat lunch anyhow, I guess that's okay. But capacitors, you can charge them like that. I mean, with the right circuit, you could put this 200 volts in there in milliseconds, and you can discharge them again just as quick. So capacitors have speed going for them, and batteries, at least with current technology, are the way to store, you know, megajoule or even gigajoule amounts of energy if that's what you need to do. There are, I only learned this a few years ago, actually. Apparently, they've been around for 20 or 30 years. There are such things as, I don't know if they call them supercapacitors, but I think they use them in electric vehicles for certain purposes. You can buy what are like 20 farad capacitors that are actually not the size of a garbage truck, you know, and that kind of impressed me the first time I heard it. It's like, wow. Anyhow, that is the page about energy stored in magnetic fields. And we have just one more topic in section 11, but we might as well leave this recording here. The last recording I made ran a little on the long side, so let's leave this one a little on the short side. And actually, I've got nothing to do for another hour. I'll probably just stop it, stretch for a minute, and make the next one.